In this video, we're going to look at 3 questions on the topic of dimensional analysis. So for the first question, it says the fundamental frequency of a drum skin has been shown to be given by F is equal to this formula, where H is the thickness of the skin, V is the speed of sound in the skin, and rho is the constant of elasticity. Units are in SI units, so the first component asks us what are the units of rho. So in this case, it says rho is constant of elasticity. So basically what we know is that F is equal to kx. So the constant is just equal to F over x, where F is measured in newtons. So newtons would say that's the mass times the acceleration, so that is kg times ms minus 2 over x, which is basically m, so therefore the units would be simply kg s minus 2. And this will be the answer to the first component of the question. And for the second component, it says determine the units of quantity A. So now we have to utilize the formula. In this case, it says F is basically the frequency. Now what we know is that frequency is equal to 1 over t. So if in SI units, the units of F would be that's s to the power of minus 1. So if we look at the equation, s minus 1 is equal to, and then 0.47 is the constant, so we can neglect it. And then over here, h is the thickness of the skin, so let's say it's m. And then v is basically just m over s. Now down there it's a squared, which is what we want to know. And then in the brackets is 1 minus rho squared. So basically the units of it will be kg squared s minus 4. And then we can solve for a. So we can time it over to the other side. Squared is equal to, this is kg s minus 2 is equal to, the s cancels out each other, so basically what's left will be m squared. And then a squared will be equal to m squared s squared and kg minus 1. So therefore a, units of a will be equal to m s kg to the power of minus a half. And this will be answer to the second component of this question. Now let's see the second question. It says the speed of surface waves of wavelength lambda on a liquid of density rho is given by this formula, where a and b are constants. Determines the units of a and b. So now in this case there's 2 variables. The units of 2 variables in one equation. So basically what I'm noticing is that they are being added together. So the only possible way for this to happen is that the units of the first term is equal to the units of the second term. So what we can do is that establish an equilibrium between these two based on the units of, or you can say the units of this entire thing that is to the power of a half. So first of all, how do you determine the units of either terms? We can look at the other side of the equation. So basically what we know is that, let's say we express in terms of the brackets is basically equal to v to the power of 2, because initially it's to the power of negative 2, the power of a half. And then so therefore the units of either of the term will be equal to m squared over s squared, which is m squared s minus 2. So basically, let's see, first of all, what we know is that for a times lambda, which is measured in m, over 2 pi, which is constant, we can say it's 1. So therefore the units of a will be equal to m minus 2, which is acceleration actually. Now this will be one of the answers. Now let's look at b. B will be the same way, so basically m squared s minus 2 is equal to 2 pi b, so we can consider it as 1 over rho is the density, which is kg over m cubed times the m. So b will be equal to, let's see, that will be m squared minus 2 times kg over m squared. So b, the units of b will be equal to kg s minus 2. And this will be answer to the question. Now let's see the third question. The third question is a bit longer. So it says, a sand timer is a sealed glass vessel with a narrow section acting as a constraint, so that sand can flow through at a steady rate. A 15-minute sand timer is shown through one below, over here, and it says, unlike a liquid, the rate of flow of sand grain through the constraint section is independent of the height of the sand above. Thus, the rate of flow of sand through time can be expressed as the product of the powers of the remaining relevant variables over here. So dm over dt is basically just the rate of change of mass, basically this rate of flow of sand. And over here we can see there's constant k, there's rho, which is density to some power of alpha times the area, I suppose, and then to the power of beta, and then times g, which is the gravitational acceleration, to the power of gamma. So okay, it says down here, it says a is the cross-sectional area, g is the gravitational field strength, alpha, beta, and gamma are numbers. Okay, so the first component of the question asks, by considering the units of variable on each side of the equation, find the values of alpha, beta, and gamma. So the equation is given over here, so basically we have to base on this equation to find the values of alpha, beta, and gamma utilizing dimensional analysis. So okay, so let's see. Let me rewrite the equation down here. So that will be dm over dt is equal to k rho alpha times a beta times g gamma. Okay, so now we express in terms of their units. So this over on this side will be kg over s is equal to k is a constant, so we consider it as 1. And over here, that is basically kg over meters cubed to the power of alpha. And then it's multiplied by the cross-section area to the power of beta times, this is acceleration, to the power of gamma. Okay, so in this case there's 3 variables, so we can't actually solve it algebraically. And then so what I'm thinking is that we can try it out in some way. Okay, so over here on the right side, what we want to establish is kg over s. So the idea is that the m's or the meters must cancel out with each other. So in this case, there is already m cubed, and then there's m squared, and m over here, so the m is already canceling out each other. And then however, the problem is that there's s to the power of minus 2. So what we want is cancel out another unit of second. So in this case, there isn't actually another term that has the component of time, correct? Yes. So the idea is that gamma must be equal to a half in order for the time to be one s to the power of minus 1. So we have established one term. So that will be let me rewrite it over here. So the idea is that kg over s is equal to kg m cubed alpha times m squared beta times m to the power of half and then s minus 2. So now what we want to do is simply to cancel out the meters. I can rewrite this as basically kg, and then because the s's cancel out each other. So how do you do this? Over here we will want to cancel out the m cubed. So in order to cancel out m cubed, beta must be equal to. So the idea is that we want to convert this into 2.5, right? So that is basically equal to 2 over 5. So basically beta must be equal to 2 over 5. Now let's see. So if beta is equal to 2 over 5, then alpha will be equal to 1. And so the answer to the first component of the question will be alpha is equal to 1, beta is equal to 5 over 2, and then gamma is equal to 1 over 2. Now let's see the second component of the question. So question B. It asks, on the moon, the gravitational field strength Gm is equal to 1.6. How long will the sand timer last on the moon if it runs for 15 minutes on Earth? So, so if we actually want to solve for k, the dimensional constant, dimensionless constant, but it won't actually be possible because we don't know a or rho. So my idea is that we can work on the fractional change in the gravitational field strength and then derive the time for the sand timer from the 15 minutes on Earth. So over here, the idea is that fractional change, so 9.81 becomes 1.6. So initially it's g, then it will be equal to g times 1.6 over 9.81. Now, then the idea is that dm over dt, let's say the new one, will be equal to dm over dt, which is basically just 15. No, it's not. Oh, it's dm over dt times 1.6 over 9.81. So over here we can actually simplify this. So basically mass actually stays the same, so the only thing that changes is basically just the t. So the dm's cancel out each other, and then what's left will be simply 1 over t, 1 over dt, 1 over dt, and then we can basically consider it as the total time for the timer. So the new t will be equal to the initial, which is 15, times the reciprocal of this, which is 9.81 over 1.6. But I did forget something. Distribute to the power of a half, because g is to the power of gamma. So we know from the previous question gamma is equal to a half. So basically, this is to the power of a half, and then we will be able to calculate the new period. So this will be equal to 15 times 9.81 over 1.6 to the power of a half, and that gives us 37, let's say 37.14 minutes. And that will be the answer to the question.